waste are discharged at a steady rate into a PFR. The waste undergoes zeroth order reaction given by dc dt equals negative k. Determine the waste concentration as a function of distance downstream from the point of discharge and time since discharge. Okay, so let's start with distance. Our governing equation for a plug flow reactor as a function of distance looks like U dc dx equals our reaction rate, which is just the constant, minus K. All right, this is an ODE we know how to deal with. Let's divide through by U and multiply by dx to get dc is equal to minus K over U dx. We're going to integrate this side from C naught. Keep in mind that C naught, instead of being the concentration at time equals 0, is now the concentration at x equals 0. So technically this is called a boundary condition instead of an initial condition. But it means the same thing, and in this case it is the same value. So we're integrating from C naught to C of x, and we're integrating x from x equals 0 to x. Okay, pretty simple integration, and you'll get C of x is equal to minus K over Ux plus C naught. Okay, skipped a couple steps because we've done them several times now. All right, let's look at this. Okay, so our concentration as a function of x is equal to the decay constant over the velocity times x plus our initial concentration at x equals 0. All right, so this is the function of concentration as a function of distance downstream. And now we're going to look at the concentration as a function of time since discharge. So just to keep this in mind, I'm going to write this over here. Now, some of you probably already see how to translate distance to time, but I'm going to do it the brute force way by using our second form of our governing equation for a PFR. Okay, so I'm going to put in this hydraulic residence time. So we have dc by d theta x is exactly equal to minus K. Right, now this is going to be exactly the same except we have no velocity in here. So we're going to have dc is equal to minus K d theta x. We're integrating from 0 to c, and we're integrating from 0 to theta x. Okay, and right away we can see that c of theta x is equal to minus K theta x plus c naught. Okay, again, skipping a couple steps because we've done them several times now, but go ahead and ask in class if you want some of the in-between steps. And now let's look at these two expressions. So before we had minus K over U times x plus C naught, and now we have minus K times theta x. But recall that theta x is exactly equal to x over U. Okay, so even though we've started from the governing equation and worked our way through, actually all we needed to do is take this x over U and plug in theta x for that term, and we would have gotten the exact same thing.